Thank you. So first, I would like to thank the organizer for organizing this meeting, this workshop in this wonderful place. I would like to say this wonderful meeting, but it's a little bit too early to say it. But I hope it will be very nice. So in the previous talk, Boris presented some nice links between automata and algebraicity, and it will be links between automata, more or less the same objects, used in a different way, but more or less the same, and something else about normality. Why is it to change the... Thank you. Yes, and it works. So I will talk a little bit about normality, just a few slides to let you wake up, because I think everyone knows. And then I will have selected 3 topics for links between automata and normality, namely first selection. We will see what it means to select digits in a normal word. Compressibility, which is a kind of characterization of normality using transducers. And something new, which is the use of weighted automata for frequencies in the output of some finite state machine. Okay, so let's start with normality. So as Boris said, I identify infinite words of digits with numbers, and I look at the frequencies of some block W in the prefix of length n of the word, and if the frequency is the expected one for all blocks, I say that the word is normal. This is as usual, so we'll skip. Just to recall you just nice examples of normal word or normal numbers, if you prefer. This is more or less the same. So, for instance, you can first there's the result of Borel that almost all are normal, and then you can give examples. For instance, by concatenating the writing of all integers in some fixed base. Here I took 10. For instance, you write 1, 2, 3, and so on, 10, 11, 12 in base 10, and you can prove, this is just an easy exercise, that it is normal. If you are a little bit smarter, you can look at squares. It's a little more difficult, but it is normal, and more difficult. There is a result by Erdős and Copeland that if you concatenate primes, then you get something normal. It's quite unexpected because you don't expect all blocks to occur in the right frequency in the writing of primes. So for me, it was quite unexpected to see this kind of result, because in primes, why should the blocks 2, 1, 2 occurs with the right frequency? It's not obvious at all for me. But still, it holds. So for me, normality is a kind of weak randomness, because this is the least you should expect from something random. Of course, if you have a random sequence, you expect all digits to occur with the same frequency, all blocks of the same length to occur with the same frequency, and actually, so that's what you expect. Of course, there are much stronger definitions of randomness, like Martin-Löhm randomness, but for me, it is the least you should expect. Okay. Okay, let's start with selection. Oh, I will slow down, because maybe it's not known to you. So what does it mean to select digits in some word? So for instance, you start, sorry, I pressed the wrong button. you start with some sequence here, A1, A2, A3, and so on, and which is supposed to be normal, and you select all but the first one. Of course, this is still normal because this is a limit. Or a little more difficult, if you only select digits at even position, it's also still normal. It's not really difficult. You just have to look at block length multiplied by 2. Or what about if you select only digits at positions which are powers of 2? What can happen? It can be normal if you're lucky, but it cannot be normal. Why? Because it's clear that you have very few powers of 2, more or less, and the density is 0. So you can take something normal, change all digits at position powers of 2 to be 0. You still have something normal, for sure. And if you select all the digits at position which are powers of 2, you will get only zeros. And of course, it will not be normal. What about if you select, let's look at the primes again. What if you select digit at prime positions? That's what you can get. It's not known so far what you will get. No. No, it's not known whether it preserves normality or not to select digits at prime position. Yes? It's not sufficient.
That it's density 0 in prime position.
Ah, yes. Yes. Yes, I should have thought about it, but I read somewhere that it was open, so I was, yes. It seems that it is closed, actually. So let's do something a bit different. Here, the position were fixed, and the input word was anyone. Here, we will do something different. Suppose the position you select, the digits you select, depend on the word you look at. So suppose you take a word over the alphabet 0, 1, for instance, and you select all digits after a 1. What should it be? What would you guess? What? It preserves normality. It actually. And if you select all digits before 1, it will be normal. We will see that later. So actually, we will look at what is called obvious selection, perfect selection. The idea is the following. You use a finite state automaton, and it will tell you whether you should select or not. And how does it do the job? The automaton, for a given digit, the automaton reads the prefix until the digit, but not including the digit. This is why it is called obvious. Otherwise, you could cheat easily, just looking at the digit, saying whether you select or not. So the automaton looks at the prefix from the first symbol until the symbol just before the symbol you're looking at, and then whether the automaton accepts or not the given word. If it accepts, you select the digit. If she does not accept, you don't select the digit. And it is what is explained here in a different way. So you select, you look at position where the prefix not including AI belongs to the set L of words accepted by the automaton. And if the prefix belongs to it, then you take that position, otherwise you don't. And if you select all this position, it has been proved by Agafonov already some time ago, that this kind of selection will preserve normality. So actually, if you take, for instance, the set of words, if the set L, of course, the set L of words is rational. So it means it is done by some finite state automaton. Of course, if L is not rational, for instance, it is some algebraic set of words, you need a stack machine, a push-down automaton, then it's something else. But actually, it can be proved that in some cases, if L is just algebraic, it will not preserve normality. But if L is rational, so it means accepted by some finite state automaton, it will preserve normality. If you take, for instance, the set of words ending with a 1, you will select all digits after 1. So it proves what we have just seen in the previous slide, that selecting after 1 will preserve normality. But you can do something different, selecting after an even numbers of zeros, after 3, 1 in a row, or anything like this. Anything that can be done by automaton, if you select according to this kind of rules, it will preserve normality. So it was proved some time ago, and it was only for prefix. Look that it does not cover the case digit just before 1. Because here you have to look at the suffix, not the prefix. Yes. Yes. Yes, I identify, more or less, I said that I identify words and in numbers, and the base is supposed to be fixed to have this identification, of course. No. Why we should not change the base? Because automata are really weak machine, and they cannot, the change of base cannot be performed by an automaton. So if you try to change the base, you will lose everything. Okay, so it was called prefix selection because the automaton was looking at the prefix. But we could do also suffix selection, actually. That's something we proved with Veronica and Pablo some time ago, is that if you fix a rational set of words, if you don't know what it is, you have, it was actually introduced by Bucci, you have automata on infinite words, and you have the notion of rational set of infinite words, and you fix X rational as a set of infinite words, and you look at all positions where, if you look at the suffix, of course not including the current digit, if the suffix belongs to X, you take that position, otherwise you don't. And if you select all the digits at this position, where the suffix belongs to the set X, then it will preserve normality, actually. So if you take the set of infinite words starting with a 1, it is of course a rational set of infinite words. It will select actually all digits which are just before 1. So it proves, that result proves that selecting just before 1 does preserve normality. But you can do something else. For instance, the number of zeros before the next one is odd or even. It could be done by some automaton, and then it would still preserve normality. Of course, when you have prefix and suffix, you would like to combine the two, but it fails. If you try to, for instance, suppose you start with a word which is normal over the alphabet 0, 1, and you select all digits surrounding by 1. So just a 1 before and a 1 after. No, you have a 1, a digit, a 1, a digit, and a 1. No, base 2. I said the alphabet is 0. Of course, the frequency of 0 and 1 will be still 1/2. But for the factors of length 2, it will fail. This is due to the fact that if you put a 1 in the middle, you have more overlaps than if you put a 0 in the middle to the blocks you're looking at. And the fact that the 1 can overlap more will imply that the frequency of 1, 1 will be bigger than the frequency of 0, 0. So you cannot mix suffix and prefix together. Of course, you can put condition but in a general setting, you cannot. So let's go further. So it was selecting. So you see, it was a nice, just to conclude about this part about selection, it was a nice way of, nice links between automata and normalities, that selecting with an automaton in a non-stupid way, so either looking at the prefix or at the suffix, then we'll preserve normality. Now we look at compressibility. So we will use finite state machine to compress. So what it is the idea? So it is exactly the same machine as Boris showed you before. So we have a finite state control, only a finite state finite memory. We have an input tape. Here we will use this kind of machine to compress an infinite word. So it means here the tape is really infinite, and we have put the infinite word as the input, and we will write something on the output. The best is to see one example. Here is the finite state machine. We have two states, and any transition is of that form. On the left, you have what you read before the bar, and after the bar, what you write. So the alphabet is 0, 1, and epsilon is just the empty word. You write nothing. So let's start. So we are in state Q0, and we read 0, and we write 0. Then we are still in state Q0. We write a 1, and we use that transition. We write a 1, and then we are in state Q1. We read a 1, and we write nothing. So the input head moves forward, but the output head doesn't move. And then we continue like this, reading a 0, outputting a 0, and so on. Okay. So that's how we use a machine. It reads the input and writes something. So we would like to compress. So we look at the ratio between when we have such a run, the AIs are the digit we read, and the VIs, what we output. So these are words. They can be empty, as we have seen, or of length 1, 2, 3, what we want. So we look for, after n steps of the automaton, we look at the length of the output divided by the length of the input, which is n actually. Of course, not to be able to cheat using a different alphabet, we take into account the size of the alphabet. Otherwise, it would be easy to write, to read in base 2 and to write in base 10. Or in base 4, which is easier, of course. And we look at the lim-inf of this ratio, and we say that the automaton compresses if this lim-inf is less than 1. And what is the... Where? I use absolute value to denote the size of this word. Yeah, yes. I mentioned that the VIs may be words, so they can be empty. Actually, I write A1, A2, AN. This, for sure, this is N, because at any step, I read one digit. So this is the ratio, and if this limit is less than 1, I said that the machine compresses. But of course, you need some additional assumption, is that when you compress a file, you would like to be able to recover the files. Otherwise, it's quite useless. So you would like that the machine is 1-to-1. And this is exactly the statement. An infinite word is normal if and only if it cannot be compressed by some deterministic, actually we will see that it can be removed by, I call this machine transducers, or finite state machine if you prefer, and here the important assumption is that the machine or the function it realizes should be one-to-one. Otherwise you could cheat and output any input to a single word, compressing a lot, but not very interesting, okay? And this is also, it's a really nice characterization of normality. Most of the work has been done by Schnorr and Stim in a seminal paper. Actually, they were not using compression, they were using martingales, but there is a nice link between martingales and compression ratio, and therefore, more or less, you get this using Schnorr and Stim. You may ask, why do you use lim-inf and non? Of course, the limit may not exist, so you cannot put limit. But why not lim-sup? A good reason is that you get that result. Okay? Of course, so this kind of result shows that exactly normal words are those words that cannot be compressed by finite state machine. So N, if you know about a little bit about randomness, you know that one definition of randomness could be those words that cannot be compressed by Turing machines. You have to take the right notion of compression, so you should use a prefix Turing machine, so where the domain is a prefix-free set, and meaning not to be compressible means that the limit of that value, this is the Kolmogorov complexity of the prefix of length n minus n should satisfy this inequality. Okay? So more or less, if what you could remember is that random sequences are the one you cannot compress by Turing machines. So these are the real random sequences. And for the weak notion of randomness we have, normality, this is the one that you cannot compress by finite state machine. So more or less you have the normal words are exactly the random, but not for Turing machine, but the random ones for finite state machines. So this is another nice link between normality and finite state machine. And what are the ingredients of in that result? Something which is easy is that if something is not normal, you can compress. This is fairly easy. This is due more or less to Shannon, is that if some word is not normal, some blocks should appear too often, and then you can use Huffman encoding to compress that word. You have to be smart enough to take the right length, because it might be that some blocks has a wrong frequency, but that frequency is really close to the expected one, and then you cannot exactly use that block length to compress. But if you use a greater block length, then for sure the frequency will be far enough to the expected one, and then you will be able to compress. So this is one way to see that if the word is not normal, you can compress with an Huffman coding, which can be achieved by a finite state machine, because it's you just have to need a window of the block length, and depending on what you see on the window, you output something. So actually you need it's kind of no memory, so it's what is called local automaton. It only depends on the amount of on some digit on the path, but not all digits, just some window. Actually, what is difficult is the converse. It's to prove that if it is normal, it cannot be compressed. So you have to prove that no machine can compress the input. Actually, this characterization is quite robust in the following sense. Of course, we have seen that to compress, you just need Huffman coding, so an easy machine, a local machine. But we have seen that if you look at a finite state machine, the transducer I have shown you, you cannot compress. A natural question is, what kind of power should I add to a machine to be able to compress something? And actually, we will see that you need to add a lot to be able to compress at least something. Because if you add just a little power to the machine, for instance, instead of the machine where I was looking at was deterministic. So on any input, there was only one possible run and of course one possible output. But I may look at non-deterministic machine, but still being functional in the sense that for any input, there is only one possible run and then one possible output. And then if you remove the assumption of being deterministic, still you cannot compress. You cannot add also counters. Of course, if you add two counters and you allow the machine to be what we call not real time, so be able to do something with the counters without using the input, your Turing complete and you can compress. But if you add only one counter, for instance, one machine with one counter, you cannot compress any normal word. So this table summarizes everything. So N means not compress, T means Turing complete, and C means you can compress at least some normal words. So here I look at deterministic machines. So finite state, that's what you have seen, with one counter or more counters with the assumption that you cannot to increase the counter, you have to consume some digit of the input. If you have one stack with one counter, we can compress. The example is quite easy. We can compress at least one word. It doesn't mean we can compress all words. At least one word. Here we don't know. This is the open question we left. If we are non-deterministic, this is more or less the same, but with one stack, we can compress. And here, this is non-deterministic and non-real time, meaning you can deal with the counters without consuming the input. And of course, then with at least two counters, you're already Turing complete and you can compress. But still, with one counter, even with one counter being non-real time, so you can use the counter in any way you want, then you cannot compress any normal word. So still it means that, of course, we can still look at only finite state machine without anything else, but still adding some memory doesn't allow you to compress anything. Of course, you can also look at two-way machines, and if the machine is two-way, with finite state control, only a finite memory, still you cannot compress anything. But if you add a counter, using the two-wayness and the counter may allow you to compress something. Okay, this is not in the table, these two-way machines. I will do some new link. This is a link between the first part and the second part. Suppose we assume the result of Schnorr and Stim. Sorry. So we will assume that the only word that can be compressed are the non-normal ones. And I will show you how we can prove easily, just using one diagram, that selection does preserve normality. So we will show in just one slide the result of Agafonov. So suppose the input is normal here. Suppose we do selection using a finite state machine. So suppose we add a little bit to the machine so that when it selects, it put the output to that tape, and anything which is not selected is put to that tape. So you, more or less, you split the input into the selected digit and the not selected digit. Suppose, by contradiction, that what you have selected is not normal. What we have seen before, you can compress. So you have a finite state machine, an Huffman encoding, that will take the green input to produce the blue output, compressing in the way. Then we would like to merge these two. Remember that we need something which must be one-to-one, because compressibility is only meaningful for one-to-one machines. So we'd like to merge these two tapes into a single tape. So we use a trick that we put a block of red, but just before we put a black one, and when we put a block of blue, we put a 0 just before. Here, 0 and a blue. For some block lengths here, I will choose it later. And, of course, selection can be done by a finite state machine, compression can be done by a finite state machine, and this merging can be done by a finite state machine. So you glue together all these machines to get a huge finite state machine, and it is one-to-one, because, yes, you have to think a little bit that since we use only the prefix, if I give you these two tapes, you can come back to the input. Compression was supposed to be one-to-one, and the merging is no one-to-one. So everything together is one-to-one. And so and here we have compress. So I have to tell you why it will compress here. We'll need a little lemma that shows that the ratio of selection is bounded by below by some rational number. So it cannot be 0. So it means that this green part cannot have a 0 density. And therefore, since this green part does not have a 0 density and it is compressed, if I choose, of course I lose a little bit by these additional digits here to be able to be one-to-one, but if I choose the block length great enough, together it will be still compressing. And I have something that compresses, something which is normal. So I get a contradiction, and therefore my assumption that this was not normal was wrong, and therefore it's another proof of the result of Agafonov, is that if you select using a finite state machine, will preserve normality. Actually, this proof is nice because if you want to do, for instance, suffix selection, you can adapt a little bit this proof to deal with suffix selection. This is just a proof by drawing. Now I will move to the last part, and weighted automata. What is the idea? So the idea is I have still a finite state machine. It will, and I say preserve normality if for any input which is normal, the output is normal. I will skip this to show you. Here is an example. So here my input alphabet is AB instead of 0, 1, but this is the same. Suppose I give you this machine with 3 states. So sometimes it outputs something of length 2, sometimes what was epsilon before is now called lambda, so this is the empty word. Sorry for the change of notation. And suppose I give you this machine, and I ask you, does this machine preserve or not normality? If I feed the machine with something normal, will the output be normal? So that was our question, and actually we have solved it in a really nice way, as you will see. So the question is, given such a machine, a transducer, finite state transducer, the question is how to know whether it does or not preserve normality. And we have used what we call weighted automata. Just to introduce the notion, I will give you an example. Suppose you have a one-letter alphabet, so an automaton of a one-letter alphabet is just a graph with weights. Suppose I give you a graph, and on each edge you have some weight, and you have one starting vertex, which is, I call the source, and one target, which is the end. And suppose for each n, which is an integer, I look at an, the sum of all the weight of all paths from S to T of length n. Sorry, path of length n. And the weight of a path is just the product of the weight of the edges. So you look at this, and it's not difficult to see that if you look at this formal power theory, it is rational. Just the usual meaning of rational, it is the ratio of two polynomials. Really easy. So instead of here you have only weights on edges, and therefore you fix the length. In weighted automata, you have on each edge you have a digit and a weight, and of course, instead of looking at all paths for a fixed given word, you look at all paths from the source to the target, whose label is the given word. So more or less, a weighted automaton is a way to compute a function from words to numbers. Here I give you one example. I lost my pointer. Here it is. Here is an example. So in black you have the input digit, and in blue you have the weights. So here they are integers, but they can be any real numbers. And you have the source, which is that state. I put a weight on that state, but since it is 1, it is as if it was the source. And here I have one target, and that's why I put a weight of 1. And if you look, for instance, at the word 110, I look at all paths whose label is 110. So there is one which is Q0. I want to read 110. So one way to do it is to read that one, then that one, and then the 0. And the weight of that path is 2. Because the first label is 1, the second is 1, and the last one is 2. So the product is 2. And I have another path, which is, I go to the Q1 with the first one, so the weight is 1, and then I read 1 with that edge and 0 again, and therefore the weight of that path is 2 times 2, which is 4. And if I look at the sum, it is 6. And 110 is the binary expansion of 6. And if it is an easy exercise to prove that if you look at this weighted automaton, if I read some binary number, the weight will be exactly the value of that number, the number I was looking at. Okay? So what is the link between normality and this weighted automaton? And it is, so it was my example. Sorry, I had a slide I could have shown you. So it was the definition I gave you. So the weight of a word in a weighted automaton is just the weight of a given word W. Is you look at all runs on W, so where W is the label of that run, and you look at all the sum. So it was my example. The sum is 6. And the result is the following. If I start with such a machine, a transducer, I can build a weighted automaton, like this one, which has the following property. For any normal input, I look at the output, and I look at the frequencies of each block in the output. And it is given, the frequency of that block is computed by this weighted automaton. First, there is a surprise, is that this weighted automaton does not depend on the input. So it means the frequency of all blocks in the output does not depend on the input as far as the input is normal. So it is a miracle. You can look at this example. If you fed it with the Champagnone word, you will have frequency of blocks in the output. For each block, you will have a frequency given by this weighted automaton. But if you feed this, the same automaton, this weighted automaton, with another normal word, for instance, the one with prime concatenation of prime numbers, you will have frequencies of the blocks in the output, and the frequency will be the same as for Champagnone. This is quite a surprise that as long as the input is normal, the frequency of the blocks in the output are all the same. It does not depend on the input. And furthermore, this frequency can be computed by a weighted automaton. And actually, here the input are blue and the output are red. And you see that in the weighted automaton, the digits are red because, of course, this is the input alphabet of this weighted automaton is the output alphabet of this one, because I look at the frequencies of blocks in the output word of this automaton. This is why the input alphabet of this weighted automaton should be the output alphabet of this one. And of course, here it is a special weighted automaton where the frequency are all rational numbers between 0 and 1, because it will compute frequencies.
If you start with a word X which is not normal, which has the property that every block computes with some
actually, this is an ongoing work. I think, yes, you can say something. But so far, I have only it for normal words. Yes. You can so it depends on for instance, if the frequency, suppose you have some word where the frequency are also given by the weighted automaton. Because you may, suppose you have frequencies, but they are not computed by a weighted automaton, you cannot say anything. But if the frequency of the input word are given by another weighted automaton, you can also get a new weighted automaton for the output, combining the weighted automaton of the input and the finite state machine that computes the output. So you have to combine frequency of the input with the machine that computes to get the frequency of the output. But if you have no assumption on the input, you cannot say anything interesting. But for instance, if the frequency of the input is a Bernoulli distribution, which is the step further after normality. Of course, it can be computed by the weighted automaton with one state, so you can do the same. And there is a nice result, is that if I give you two weighted automata over real numbers, or rational numbers actually, you can decide whether they compute the same function. This is not so straightforward actually, because you need the fact that the weight you use are in a field. If you use, for instance, if you use a strange semi-ring like the tropical semi-ring, it's not true that you can decide whether two automata compute the same function. But this is true, and we're using this fact, we can decide whether a deterministic normal, whether a deterministic transducer will preserve or not normality. How do we do? We start from the transducer, we compute the weighted automaton that computes the frequencies, and then we compare it with the weighted automaton that compute the expected frequency, and comparing the two allows us to check whether the transducer will preserve or not normality. So it was my last link between automata and normality. And I think I will read just to conclude. So we have seen three links: selection, compressibility, which is a kind of characterization, and this link between the frequencies of output of transducer with normal input and weighted automata. I stop here.
Can you just as your research or finite automata give a one general class of machine that cannot compress normal number?
So you mean just the compressibility?
That's finite automata, but I study the automata, but the state is not finite. Linearly, it is zero finite.
So
in some conditions that can also have the same property that cannot compress finite automata.
Actually, the problem is that if you are, so this is what we, is it that what you're talking about?
Maybe that class, I consider automata, that is the number of states is not finite.
Ah, yes, I know what you mean. So, yes, I know what you mean. So you have the condition, for instance, the set of accepting sets is finite, for instance. So far, no. If you have what we use, the fact that we have used the fact that here, for instance, if you have one counter, the number of states is infinite, but we use really how the memory is used by the automaton. So really, if you just tell me that I have infinitely many states, without, here we use really the way the memory is used by the automaton. So far, we have not been able to generalize to any class of finite state. Of course, if you have no constraint at all, it is true that it will not preserve normality. So you have to add some constraints. So far, we have not been able to add a constraint that includes yours, for instance.
You're talking, so normality in the state is related to non-compressibility.
Yes.
My question is, how about the beta expansion?
Actually, with some students, we did a word on shifts. So instead of here, I was looking at all sequences over some alphabet. So instead of looking at this, you can restrict the domain of some shift of finite type, for instance. And then still you have the same result, that you cannot compress inside the shift if and only if it is normal for the Parry measure. But you need, we did only for shift of finite, Sophic shift also. It works also in Sophic shift. So depending on how your beta is, if the associated shift is Sophic, it will work also. Yes. Yeah, yes. You have the same property that being normal for the Parry measure is the same as not being compressible. Actually, this is yes. That's something we would like to look at. Actually, we have one student starting that will look at this. And for instance, if you start from if you select only the digit at odd position, for instance, something really easy, you can show that the discrepancy, if you start from some discrepancy, you have to put a square root on top of the discrepancy. So, and I assume that if you do with an automaton, it will do more or less the same, but instead of, it will raise the discrepancy to some power, which is a rational number given by the automaton that does the selection. That's what I suspect. But it is not proved so far.
Yeah.